So I'm going to show how one can extend the current geometry features in 10 to compute eigenvalues over what really are arbitrary regions, or eigenvalues of elliptical operators over these regions. So as you've all seen, in 10, of course, one can now do PDEs over very complicated regions. This is a fairly simple one, right? And it's fast, okay? So it's quick and easy to solve, say, the Laplace equation over this kind of domain. But currently, with built-in methods, I could not solve the eigenvalue problem over this domain. Okay? So you can use the geometry features to do that, but you have to do a little work yourself. And basically what I've done is I've implemented, right, really the usual finite element method for the eigenvalue problem here. So, right, we have a differential equation here that we want to solve over some region, right, script r, okay, and right, we generate the weak form of that equation where t sub s is some test function, okay, and I'll discretize r with first-order triangular elements. So on each element, we approximate the function psi by some alpha I of x and y times psi I, where psi I, right, is linear in x and y, and the a i's are given by these combinations, right, where, right, this will refer xi, yi, and so on, right, depend on the vertexes, okay? And so we can write the alpha I as, right, like so, where A is the area of each triangular element, okay? So this is just the usual finite element method, and then I'm going to pick my test function as alpha of x and y, okay? So the whole trick is we can compute these on a reference triangle. This is what's normally done in finite elements, and then we'll push that across the vertices of all our mesh, okay? And we can do this as a essentially vector operation, okay? So it's very fast and efficient. So the end result is that for each element, right, we have a equation which looks like this, where, right, s sub, right, delta here indicates that this is the integral over the triangle, right? And here's t, which is also integrated over each triangle, okay? So the s's and delta, or and t sub triangles are all 3 by 3 matrices, okay? So for each mesh, right, for each triangle, we're going to get a 3 by 3 matrix. These are local matrices, and then they have to be assembled into a global matrix, right, S and T with no subscript here, okay? And these will be n by n matrices where n is the total number of nodes. Okay? And then we go ahead and we solve the generalized eigenvalue problem, right? S psi is equal to k squared t psi. Okay? So, right? Okay, so let's look at an example, and I've picked a hexagon as an example because I have colleagues who sit next to me at the University of Cincinnati and some in Australia who do not sit next to me, obviously, who grow and study. They're actually grown in Australia, studied at the University of Cincinnati, among other places, what are known as core shell nanowires, and these are more or less hexagonal. Okay? So here we have a hexagon. I just generate the boundary points, and then I form a boundary mesh region, okay, from this hexagon, and then I have to tell it, right, what order I'm traversing things in, and of course, right, I have to close it up. Okay? So I generate that, okay, and right, okay. I can then generate a mesh, so I can triangulate it. And this, of course, is normally one of the hard parts of finite element, but I'll just let, right, the function triangulate mesh do that. Here I've set the mesh quality goal, right, to maximal. One can do, in fact, much finer mesh if you like, and we will need to later. Okay? And I also need to compute the boundary mesh because I'll need to specify, right, the boundary values at the boundary. Okay. So here I'm showing you the mesh, right? The red are all the free points, okay, the free vertices. Everything in black will be specified by the boundary values, right? And they're all, right, numbered here as well. So not only do the new geometry functions make it easy to specify a mesh, they also make it easy to visualize it and play with it. Okay. So what do I have to do now that I have my mesh? Well, I have to compute, right, the alphas essentially, right? And right, so the code is more or less literally a translation of what was on the first slide, okay? Written so that we can push this, right, across the elements here, right, and compute, right, S for each triangle. So this SEL here is the element matrix for each triangle, and TEL is also the element matrix for each triangle. And this actually depends only on the area of the triangle. Okay, so right, our triangle areas, right, computed here. It's just a long list. We can then simply compute T for the whole thing. Okay, so we now have to assemble a global matrix, and this is best understood, okay, with a little example, right? So I made a very tiny mesh region here to make it easier to understand how the assembly is done. Okay, right. So I've got 1, 2, right. Okay, 3, 4 triangles which are labeled here, and then the vertices are shown in red. Okay, so the 2 here indicates dimension, so that's going to label the triangles. 0, of course, will label the vertices. Okay, so I'll extract the mesh cells from this mesh. Okay, right. So that extracts the polygons. Okay, then I can extract a set of indices from those just by, right, getting rid of the polygon. So these are the indices. So for instance, my first triangle, right, 1, 2, 5. Okay, second triangle is, right, 2, 3, 4, and so on. I'll need a list of global indices, right, which I can get simply by taking the outer product, right, of the indices. Okay, and then, right, we should check, right, the dimensions of that. Okay, so the dimensions of the global, right, are, right, we've got 4 because we've got 4 triangles. Each of them are 3 by 3s. Okay, and right, in order to assemble our global matrix, okay, the rule is that Sij element, so E here stands for element, and the I and J stand for the vertices, for the indexes of the element matrix. So this is, each of these are 3 by 3s. They get mapped to N of I element, N of J element, okay, where NEI, for instance, is the global node number indexed by the element number and the local number, right? So N of 2, 3 is 5, since that's the number of the second node of the third element if we go around, right, counterclockwise. Okay? So this is just really a replacement rule, so it's fairly simple to write in Mathematica. Okay? And I've got a little function called generate matrix which does that. Okay? And now, right, we just bundle up the code, and the code looks kind of bad and long, but right, this is just essentially standard, the standard finite element stuff. The function, right, here, right, called coordinates, right, simply fishes out the 3 by 3 coordinates, right, the coordinates of each little by looking at the mesh cells and then picking out the mesh coordinates of those cells and bundling them up, right, so that you've got the cells of each triangle, okay, or the coordinates of each triangle. So this is an old and slow machine, okay, but even on this old slow machine, for the mesh you saw this took 0.2 seconds, so it's really quite fast. Okay. Right. Now one thing that's happening here, okay, is that all the, right, if you look closely you'll see that I have things labeled free points, right, and then they're boundary points. So when I generate this large matrix, capital S and capital T, okay, I then decimate it along from the boundaries, okay, so that I remove those entries. And that way, when I'm solving, right, for the eigenvalues and eigenvectors, okay, I'm solving a smaller system. Okay. The small element matrices, right, SEL and TEL, are generated as sparse matrices, okay, since, right, they get essentially blown up to n by n dimension and then added together to generate the full matrices. And now here I've plotted below, for instance, the ground state here, right, for my hexagon. Okay. Now, actually, when they grow these nanowires, they're not really hexagonal. Okay. So could we do better? Okay. So here we have, right? So the ultimate goal actually is to do this from a TEM, high resolution TEM pictures. Okay. But to see if it worked, I simply sketched this, right, on a piece of paper in my office and photographed it. Okay, so here we've got a core shell nanowire grown by a particularly inept graduate student. And my collaborators assured me they'd fire such a graduate student who grew something like this. Okay, and in a real core shell nanowire, what you have is there's a potential here that's different from the potential here. So we'll want to be able to put a potential on the center there. Okay. So, okay, if I was really good at image processing, then I would simply use the image processing tools in Mathematica to extract the boundaries. Okay. I'm not really good at image processing, and I found that, okay, I had to laboriously tweak the code for each particular case, okay, to really get at the boundaries. So what I did was I simply clicked the points off the boundaries. Okay. Okay. Those were the long numbers that, right, you saw it takes, 2 minutes or so. It's really straightforward. Okay. I make it cyclic by adding the first point at the end. Okay. So I get cyclic boundaries. Okay. So here are my two boundaries. Okay. Well, or the points that represent the two boundaries. Since they're nice and cyclic, right, I can simply go ahead and use boundary mesh region, okay, to generate boundary meshes for those. So I have to give it the list of points, and then of course I have to tell it how those should be connected. Okay. The other thing one has to do is, of course, to scale the data, because this has been essentially just grabbed off a picture. Okay, so I scale these so that I can put them together. Okay, and the scaling is done so that the x coordinates lie between x min and x max. Okay, and then I'll show you. So we scale the boundary regions. Okay, and triangulate. Okay, so there's the outer regions, gotten from my picture and triangulated. Okay. Okay. And I need to be able to pick out the mesh cells that are in the inner boundary because they're going to have a potential on them. Okay, so I'll generate a region member function, okay, and then I'll simply call you in that region if, for example, the centroid is inside the region. Okay, so if you're a triangle, we compute your centroid. If it's inside the region you're in, otherwise you're out. Okay, so this gives us, for instance, the cells in the region. Okay, and this is still a relatively small example, so right there they are, and we can get the cell coordinates from them. Okay, and we need these to compute the areas of the cells. Okay, so here, for example, are some of our cells that lie in the region. Okay, and I can visualize that right by making these graphics objects. So here we go. I'll combine them with the outer boundary region. Okay, so you can see, of course, we do particularly poorly because right we don't have enough polygons. Okay, so right we need to do better than that. Okay, in fact, I'll show you the right. Here's the boundary we're trying to approximate. Right, so we want to refine the mesh. But we only want to refine the mesh around this boundary, right? We don't want to refine the mesh everywhere. That just wastes polygons, right? And thus will lead to a much larger matrix to find the eigenvalues of, right? So we'll write a mesh refinement function, okay, which uses the region distance and region difference here, which says, you know, if you're close to this black line, I want to refine the mesh. And so then we'll triangulate the mesh again. Okay. And right here you see we've got a much denser mesh in here. We haven't done anything out here. The refined mesh does right a much better job. Right. So here we have the boundary points on which right that I extracted from the picture. Okay, shown in green and red. And now, right, all we need to do now is to put a potential on. Okay, I'll need the dimension. Okay, okay, and so I just pick out the selected cells, the area of the selected cells. Okay, since my potential is constant, right, it's piecewise constant. The matrix elements here are just my old T element up to right a constant. Okay, so basically it's already been computed, and all I have to do is to multiply by that. Okay, do that for the whole thing. Then set a potential. Okay, so now if I wish a new potential, right, I only have to change one number. I don't have to do any computing, so I've bundled all this together, right? And we run it, and it doesn't take very much time. Okay, and right, okay, and this does take a second or so, and if I don't rerun it for some odd reason, I get this cluster integration label here, which I do not understand, but okay. Nevertheless, it works. So right, here we see the excited states, okay, and I'm only showing you right the first 5 or so. If I need more states, of course, right, as I move up in state, my error gets worse, so I'm going to need right a finer mesh. One can also do this with a potential that's not constant. Okay, simply by saying, well, my polygons are small, it's constant over that polygon, right? So I'll just right take the value of it at the centroid, okay, and then map that across my polygons instead of mapping a constant potential. Okay, takes essentially the same amount of computation time. You only have to be sure that right your polygons are small enough so that the potential doesn't really vary in the largest of the polygons that you have in your calculation. Okay? And if that's not true, then you're going to have to refine the polygons, One could, of course, write a mesh refinement function which depended on your potential and thus, right, automatically ensured that the polygons were refined according to the change in the potential if necessary. Okay. And when I've done this for the Schrodinger equation, you could do this for other equations. I'm using linear, right, interpolation and triangles, right? It would be better to use quadratic interpolation. You'd get, right, much better results in terms of accuracy. But I haven't done that yet.